we have all these areas that are specializing for objects that are very important for us. Faces, body images, objects, and so on and so forth. So what we wanted to do next is say, now they can recognize a tool, they can recognize a face, they can read using this method. What happened when we give them this information using the sound? Would they develop the same selectivities? Where it will be in the brain? So the first thing we did was we did this sonification for objects, yeah, in this ventral stream. You remember we had an area that responds to visual objects, this ventral stream, this basically half of the visual system, yeah, responds for objects and tools. It responds also to touching objects and tools, but it's not responding to sound. But this was because our hypothesis was that the sounds don't contain shape information. Now we can go and teach them to build the geometry, build the objects, and recognize them using sound. And what happened was pretty cool. We had two big groups of subjects. And this is this 2007 Nature Neuroscience paper. One group, and several follow-ups after, one group included congenitally blind, late blind, and sighted people that learned this algorithm and really learned to do, like you started the training, yeah, but they did it for 40 hours. The second group were giving the sounds. Let's say they give this sound, weird sound. We tell them this is a face. It's a general association study. Another sound with we tell them this is a hammer. But we didn't tell them about this algorithm. Yeah? And what we found was pretty amazing, that in all the individuals that learned to extract the shape and build really the geometry, all of them recruited the ventral visual stream. Congenitally blind, late blind, sighted. All the people that learn association, none of them recruited the ventral stream. So it's really an operator that build the 3D and the 2D of the environment and do the combinatoric of building all the information into something coherent. And this is why we can reprogram it in the adult brain. We can reprogram it in the... Okay, the second area that we studied was this very, very interesting area, which is called the visual extrastriate body area. This area was discovered by Nancy Kenwicher lab in MIT, and it was published in Nature because it's a very important area. Why? I will show you in a second. So we think that faces are so important, right? And we can understand the other people by looking at their faces, right? I can see now that you are bored, yeah, or excited, or I hope more, yeah? But the body, we don't pay too much attention to it, yeah? This is actually, we need the presentation. So what you saw there is two soccer players. Unfortunately, I don't have Messi here. But basically, one of them scored goal, and one didn't. And you need to tell me who you think scored the goal and who didn't, okay? Yeah, great. Here. Who think this guy scored the goal? Raise your hand. Okay, a few. And who thinks this guy scored the goal? You have to decide one. Okay, so actually I lied to you. Both of them scored the goal. But if you have the information from the body, you can understand this, right? Better than the face. And the opposite, if you look at, we like to see Ronaldo in a missing position. When I give this lecture in Madrid, I put Messi missing. But anyway, no, I'm just kidding. But okay, this is the visual information. Now, why this area is so important? Did you hear about the mirror system? The mirror system is a very important system that is very well preserved in evolution, that was found by Rizzolatti from Italy. And this system, basically what it's doing, it have their neurons that respond either when you looking at an action, okay, or when you do this action yourself. It's this, the neuron responds the same to both modes. One looking at movement, one doing the movement. One looking at the body posture, and this actually explains how come babies, you all, I guess, experience it with your, sons and daughters or nephews, and that they take the phone and they know how to open the home screen. How they do it, they look at you, do it, and they have this mirror system that match the vision into their own body, and they execute it, okay? And you see even a monkey can do something like this, yeah? And what I want to show you here is that this ability to match the visual and the motor and the body is very well preserved in evolution. You can see here this cute kitty, yeah? Can we... So see, there is the movement, he see it, and he moves the hands and the body according to it, right? Now, it's so well preserved in evolution that even humans can do it. Yeah? Now, you know, I'm a serious scientist, so I did a very thorough YouTube research, yeah? And I actually found one example that don't fit the theory. And this is this dog. Yeah. So, but like a good scientist, if it's not fit my theory, I take it out. No, actually, after I show it in some presentation, I started to get angry emails from people that, I have a dog actually, I love it. Her name is Papuka, but, and she's very smart, but I started to get angry emails from people that have dogs, that they can also do it. And one of them actually sent me this movie that really convinced me that, oh, yeah, never mind. So they actually can do it. But now, actually, what about blind people? They don't have access to this because the main input to the mirror system is this visual extra-striate body area that was reported in Nature by Nancy Kenwisher. But now we can actually, and I actually already showed you this movie, of Hamutal listening to the soundscape, build the image in her mind eye, and doing this thing. Okay, now where in the brain does she have this activity? What we found is that what you see here is sighted people looking at different body posture, and we contrast it with faces, with reading, with all these other categories within the visual system. What you see here is that 100% of the individual have activity in the right visual extra-striate body area. But here is a group of congenitally blind, again, never see one photon of light in their life, and they recognize the body posture like Hamutal was doing by the soundscape. And the peak in 100% of them is exactly in the same place. And this is the overlap of the two. 100% of all the subjects show activity exactly in the same spot in the brain with visual experience, doing it by vision, and without visual experience. So this is a very strong evidence that, again, against this concept of critical period, the window is closed and nothing can be done anymore. We can reverse it. And now there are people that try to reverse it also with other things. There is a group in Harvard that show that you can do some pharmacology. You can give some pills and some pharmacology and open the brakes on critical periods. But this is a very simple thing. It's not simple, yeah, but 40 hours training, and you can also open without doing stimulation, without giving drugs. You can also do it. So I think it's very interesting. And what is even the most strong evidence, I think, is that if you look at the peak activity in the brain and you don't tell me if it's a blind doing it by vision or by sound and sighted doing it by vision, we cannot tell how he did it. We just know that this is a body analysis, okay? So the take-home message is that our data suggests that visual cortices do not need visual experience to develop specialization. And basically all these areas can be reprogrammed in the adult brain. And we think about the brain as a computational devices that one sense is usually better to perform the activity, but actually if you are creative or you teach the brain, it can do other things. Now, I don't know, I think there is one more, we can finish here, or I can share with you one more piece of line about reading, which was, I think, 5 minutes? Great, so let's do it in 5 minutes. I think it's a very interesting case of another evidence that's showing us that really the brain can develop visual specialization in any age. And it's true with this technology, but also with braille reading and so on and so forth. So let me share with you this last piece of evidence, and then we can finish here. We also, you can see here a sonification of Marilyn Monroe with 1,700 pixels. So you can see that this method can be quite high resolution, but the difficult part is it's very demanding cognitively and require a lot of training. And now we develop, before I would finish with this reading thing, one of the difficult things is that if somebody wants to learn it, he needs to come to our lab. And that's a problem, right? So if we want to scale it. So what we did, we developed two new technologies that I'm going to talk about in Bilbao, in the ophthalmology conference. And we also hope to bring it into the blind people all over the world in the next year. We developed two types of technology. One technology, I don't have time to show you all the movies, but if you're anyone interested, I can send him all the movies and all the links and the papers. One is a cane that is about this size, a bit bigger, that have a camera inside. And this cane, when you get into closer to objects, starts to vibrate, okay? So it basically gives you with touch what we did here, but it's doing two more things. One, it's have an artificial intelligence chip in it, and it's not just vibrate, but because it can vibrate from the wall, but it can also vibrate from a person, right? So it also tell you a wall or a person or who is this person or an object, okay? So it's basically telling you what's in the world around you. But then at the same time, you have another, you can switch it, the sonification method, and it tells you a person or a chair, but give you also this very complex iMusic sonification, and they can teach themselves now. And they can go and palpate things and then listen to them, okay? The second technology we developed is glasses that can do a lot of objects at the same time. And we reprogram speech in a way that just by hearing Carol, I know where it is where she's located. Because you can have high pitches of the sound, low. You can have the relative between the ears. If she's on the left, it's come more to the left ear. If she's just in the middle, it's come to both ears. If she's on the right, it's come to more to the right ear. If she's up, it's high Carol. If it's low, Carol. Laptop, and so on and so forth. So they can have an understanding of the entire scene, top down, and now they can also get the information of the sonification and teach themselves. So this is like in a nutshell what is in the technology, and I want to finish now with this example of reading because I think it's a very important and very interesting, and you use reading I think in optometry a lot, so I think it's actually one of the things that's studied the most. So I want to start by saying that how do the brain, we all the time develop new technologies. Now it's coming every week, but before it came every several thousand years, we have a technology, the wheel, invention of the reading, and so on and so forth. And the question is, how do the brain adapt to new technologies? So usually how it's happening, what the brain did is that as we needed more and more brain real estate, we did more gyroses and sulci. So gyroses is mountains, and sulci are the valleys in the brain. And the reason we have all these more and more curves is because one solution was to increase the brain all the time, yeah? So that's what happened in evolution. But the problem is that you need to give birth, right? So when you need to give birth, then you are limited. At some point, it could not grow anymore. So the solution of the, I can take it, yeah? The solution of the brain was to do this. And now you can give birth very easily, right? So all this is the gyroses and the sulci, okay? So this was one solution to the real estate problem. But at some point, this explains with things that are in evolutionary time scale. So, for example, we have area like Broca and Wernicke that, and by the way, the same thing as evolution. When we have evolution, we started with animals with flat brain, and as the evolution become more and more complex, the animal. Also, it's a very important principle of Darwin. When we are babies, we do fast forward evolution. We have a flat brain, and then more and more and more complex. He said it in a different thing. I generalize it to the brain. So we actually redo evolution when the brain develops, when we are babies. And what is really interesting is that if we are trying to think what are the technologies, we don't think about language as a technology, but it's actually a very powerful technology that developed that about 100,000 years ago. We have this ability to coordinate things and to hunt together and, to coordinate the civilization of humans. This was a big invention. And in terms of evolution, 100,000 years is enough to develop brain area that specializes in language, like Broca and Wernicke. So this is why all of you in the room, and in China, and in Israel, in Hebrew, in English and Chinese, all of us have the same areas, same location. If I'm going to put you in an MRI machines, like I show you with the blind, you all have the language area in the same place. Más o menos. But what is really interesting is that writing and reading was invented together with the wheel about 1,000 years ago. About 10,000 years ago, yeah? So, in principle, 10,000 or 5,000 years ago, it's nothing in evolutionary timescale. Yet, Stanislas Dehaene, together with Laurent Cohen, found that there is an area, if I take all of you, and it doesn't matter in which part of the globe, and which language, and scan you, you have a reading area, which is called the visual word from area, and it's in exactly the same location in all of the individuals. So the question he asked basically is, how can it be that we have the same brain area when there is not enough time for evolution to develop brain area like this, okay? And the solution was that maybe there is the theory called recycling theory. Maybe we were recycling so this area was doing something else, and we recycle it. So what do we know about this visual? By the way, this visual word from this reading center is always located between the face area, the fusiform face area, and the tools area that we talked about, the LOC, the visual object related area. Always in every one of us. And when we learn to read, it suddenly emerged between, in the beginning we don't have this specialization, and when we learn to read when we're 6, it suddenly emerged in between the face and the tools area. So what do we know about this area? What Stanislas Dehaene found when he scanned it is this area really like the center of the field and not the periphery. And he really liked line junction. Now, if you think about it, when you need to read, you need to put the focus of your vision in the fovea, in the center, and you need to analyze a lot of line junctions. So this theory was a very, very beautiful theory. And one day when I worked with José Sael from Institut de la Vision, I went to visit Stan, and he showed me this beautiful theory and the results. And I asked him, basically, Stan, this is a very nice theory, but we have all this data about the sonification method and so on. What do you think happened in Braille? Because in Braille, and congenitally blind, people that were born blind, and what we, basically, when you're congenitally blind, we cannot talk about fovea and periphery. And also there is no line junctions because Braille is from dots and touch. Where do you think we will get the reading center in congenitally blind that read Braille? And our hypothesis was that maybe it will be in this yellow areas, the touch system, but you can already guess what was the result. What we found was pretty amazing. The peak activity of reading in congenitally blind that read Braille falls exactly in the same location as the reading center of sighted, and they don't have any visual experience, no fovea, no line junction. So it's actually what we showed later, and I don't have time, but we showed that if you can teach Braille to sighted people, it will fall in the same area. You can teach people to read 3-letter words with the sonification method, and in 3 hours they develop the selectivity. And what we actually think about now is that actually, if you think about it deeply, reading, which is one of the biggest inventions in human civilization, is actually a sensory substitution. Okay? What do I mean by sensory substitution? In all the years until 10,000 years ago, or 8,000 years ago, we communicated only by audition, right? So we have phonemes, they connect to words, they connect to sentences, and this is how we transfer meaning. But the problem is that we cannot keep the history, we cannot keep the knowledge, we cannot move the knowledge from different places. So the invention of reading was actually taking, in the beginning, a whole words, a whole objects, and represent them with visual symbol on a rock. Now you have a visual representation of something that is auditory. A word for a word, an auditory word, a visual word. This is reading. It's actually a sensory substitution. Like we took the visual input from the eye and embed this information in sound. Here we take this information from audition, embed it in vision. After that, we had invented the phoneme system, which we don't need a picture for anything in the world. We can have just 22, 26 phonemes. The phonemes are represented by vision, the different letters and the vowels. And now we can transform it to the language system and have meaning from vision and not from audition. And actually what we suggest that the visual word from area, and we wrote a review together with Stan about it, it's an area that can analyze any shape, like we showed for touch, like we showed for sound, any symbol. But what this area have is a very unique connectivity that we discovered that connected into the phonology and the semantic system, this auditory system. So it's know how to go back and forth between the visual representation and the sound representation that give the meaning and the language. So this area have nothing to do with fovea. Okay, we use fovea and so on and so forth. So I think, and then later if you think about the number, it's a sensory substitution for quantity with a symbol. The note system is a visual representation of the sound, height, and Braille is a double sensory substitution. Braille take a sound, phoneme, and words. It's embedded in visual symbols, and then the visual symbols are translated into touch, but they are all representing the same thing, the vowels and the words that gives the meaning, okay? So this is like a new way to look of how the brain is organized. It's not about the senses, it's about the computations, it's about the connectivity, it's about what is the function that it's doing. And if we understand that, we can use the other senses much better in order to do rehabilitation, whether if it's a cochlear implant, it's a visual implant patient, it's a cataract, it's congenitally blind, it's somebody that is going to lose his vision, and we can play with this cane, with touch, with sound, in a way that will help us clinically to do rehabilitation. And at the same time, it suggests a new theory about how the brain is actually organized. Thank you very much for staying with me so long in this hour, and I think I don't know if you want to take some questions, or I don't know.
Lo primero, agradecer la...
First of all, I would really like to thank you for your presentation. That was amazing. Secondly, why is it that people who are still partially sighted, why is it so difficult for them to learn Braille?
The reason it's difficult to learn Braille is it actually relates to the history of how Braille was invented, okay? I don't know if all of you knows, but the reason Braille was invented was started by Napoleon, okay? So Napoleon, they have a lot of situations that they have to fight in the night, and they have to fight, so he challenges officers to come up with a system that they can have orders delivered without speaking and delivering one of his officers, Charles Barbier, invented a 16-dot system to do it. And he was very excited from his invention. He came to Napoleon. They tried to teach all the officers this, and it failed miserably because every letter took a lot of, it was big because they needed to discriminate it with touch, and it's a very long process. So he was very frustrated, and it's dumped. They never used it. And one day he visited Paris. And in Paris, he met Louis Braille. And it was actually the first institute that was trying to help blind people and low vision people. He himself was blind. And Barbier said, I invented it for this, but we don't use it. Maybe the blind people can use it. So Braille took it to home and think about it for a long time, and he decided to make the letters much more compact, only 6 dots and not 16, and much smaller. It fits the tip of the finger. But the distance he chose was the minimal distance that we can discriminate 2 points. It's like 2.3 millimeters. And so it's very, very difficult. It's like almost below, like if you put it a little bit closer, nobody could discriminate the dots. On the other hand, if you manage to discriminate the dots, you can read very quickly a lot of information. So I think the reason it's very difficult for low vision people and for sighted people to learn is because it's just on the JND, on the just noticeable difference. And you really need to invest the time to do it. We run a project together with a group in Poland that are very good at teaching Braille. And we showed in an eLife paper that anyone, sighted, even sighted people, we run a group of like 40 sighted people, do a proper Braille course. Everyone learned it and read quite fast. And we found that they recruit the same visual word from area. And if we, as like the sighted and the blind, the sighted people, and also if we use TMS and we interrupt the activity there, we interrupt them for reading Braille. So what we do now, we actually develop now a new language that is a combination of Morse and Braille that is auditory. And it's still a pilot, but we showed that in 10 hours, you can have people reading with sound as a whole Twitter in less than 1 minute. And they learn it in less than 10 hours. So again, I think the challenge here is to understand, first of all, sorry that it's a bit American and kitsch, but almost everything is possible if you really understand it. And then you need to adapt the technology and the training and the rehab to push the system in the right direction. So it's difficult because of the JND, but it's possible, and maybe we can change things. We can find the more optimal, maybe increase it, maybe combine it with touch, maybe do something else like with sound, that anyone can learn it much quicker. But low vision, and they should be encouraged to learn Braille, and this data, and I can share with any one of you here, showing that even sighted people, not low vision, anyone can learn Braille in a course that is very structured and with good teachers. Yeah? Oh, just a saying.
We need the person to use the microphone.
Yes. Yeah, so Neil Harbison, for those of you who don't know, for those of you, I would tell to the people that don't know, he presents himself as the first cyborg. Yeah, he's the first person that put electrode inside his brain. He, and again, I don't know how much it was studied scientifically. He's a wonderful speaker, and he took it very seriously. What he did was actually very similar to what we did in sonification, but much more simple. What he did, he have a camera here, just like our subjects. He take the image, and it's doing the average color of the entire image. So here it will be, all of it will be nonsense, yeah? But if I'm getting closer, so this would be white, right? And this would be blue, if I look at your jacket, and this would be red, yeah? And then he associated different height of sound for the color, okay? So he did something very simple, but not with the whole image, not with 1,500 pixels, only 1 pixel, and he can know what is the color. He could have also a much more simple thing that it will tell him what is the color, but it's interesting because it's a sensory experience, and the way he described it is that after he used it a lot, he really can discriminate very, very fine colors based on the sounds, on the height, on the pitch. So it's like taking the spectrum of 400 to 700 and doing a pitch, a very accurate pitch for each one of the part of the spectrum and know what is the color. So in a way, we say the same things. The technology, I think, is a little bit different, and also the science behind. And I think one thing that I really like a little bit less about his words, and he looks and he presents much better than me. It's a very, it's an artist. He think about it, and I think one thing that I liked a little bit less in this work, if I may, is that his claim is the first cyborg, but actually the electrode he put in his brain that gives is actually not touching any neuron. So actually, you could take this part out completely and just listen to the sound and the vision represented to the sound. And he actually also has vision, yeah? So he's only colorblind, so he can see the colors using the sounds. Conceptually, I think we're saying exactly the same thing, yeah? That you can be creative with the technology and try to do bypasses, and the brain would pick it up if you use it enough and it makes sense to you and it's helping you, the brain would pick it up. What specialization you have in the brain, I don't know. It's a very interesting question. We run now a project that is similar but using a more sophisticated algorithm, and we see that you can create a whole new tone map that fits the visual image if you train on something like this. And we also know that there's people like Kandinsky that have synesthesia, that have this merging of the senses, this neurological condition, that when they listen to different sounds, it triggers automatically different visual experiences. And in case of Kandinsky, it was different music created different color experience. And some art historians actually claim that Kandinsky's images are so colorful. He actually writes in his diary that he always put music when he draw, that maybe it has something to do with it. Okay? So I think you were amazing. It's 10 to 10. In Israel, everyone would be asleep. Okay, one more? No problem. I can stay here until midnight.
Yeah.
I'm good, but okay.
Yeah.
Oh, just a second. Can you ask it in English? Or?
Yeah, of course, no problem.
I would then trust. Okay.
See?
Yeah, I would repeat it. They would translate me because it doesn't work for me.
Well, I'll just do it in English. Well, first, thanks for your presentation. It was either amusing and entertaining and close. And those two things at the same time is not easy. So thank you and congrats for that.
Gracias.
And my question is, I understood how your sound-based system works for 2D images with pitch and time. And what's the plan when we're talking about non-static images? When we have like continuous vision.
Right.
How do you represent that?
Right. So first of all, you can do, with our algorithm, you can do, so the question was, okay, it's all very nice for scientific reason, and the reason we built it originally was to understand the brain, okay? But you're coming from a background of we try to help the people, right? So let's try to see how there is also limitation. And I try to be very honest about the limitation. It's very demanding for the brain. It takes a lot of time to learn. It's like learning a new language, and it's slow. So if somebody is walking to me slowly, it's fine. But if something is moving quickly, like a car, it doesn't work, okay? It's not good. So how do we deal with this? So first of all was what I told you about developing this cane, that you can navigate with it, and you get the feedback automatically, and it gives you the distance to the objects. It gives you what it is. It tells you what is in front of you, and it also gives you the sonification if you wish to learn. That's optional. So that's one thing we did, which is practical, and we hope in the next year to bring it into the several pilots in several places in the world. Maybe this would be one of them in Spain, and we hope this would be, and it's actually pretty cheap. It's not a 100,000 euro surgery. It's like $200 device, yeah, or maybe less. The second thing is we try to improve the sonification method, and some other people in the world try. So one thing we did was we added the depth information and the more instantaneous information that you will get some part of the vision of where you look at. And the way we do it is by, if the object is very close to me, the sound will be very strong. If I'm getting far away, the sound would go down. And you can have only part of the image, but more instantaneous. Another thing we play with is we created a glove in two sides of the hands, and it gives you some additional information, and touch is instantaneous. So we don't have yet one ultimate solution. We probably never manage to really replace vision, because there is a reason we have, over 1 million pixels in the brain and so many neurons and so on. But maybe like reading, like Braille, like some of these old technologies, at some point, also Braille was not accepted when it was introduced, for example, in the States. And it was considered rubbish in the beginning. And suddenly, it gained enough momentum, and the training was better, and suddenly, boom, in like 5 years, it exploded in the world. So we need to find this sweet spot to start having, and it's a difficult market, because when we try to do like a startup company to create some new technology, all the investors say, the market for this is so small, blind people, how many, So we need somehow to join forces, organizations that want to help people that are low vision or very severe vision and congenital, people that lose their vision, people that knows that they are, even psychologically, even if you help them only in 5%, but you have something to deal with while you're losing your vision. All these things I think is very important, and we have a lot of work to do. And we hope that besides understanding the brain a little bit better, we contributed something into this effort. And I'm here because we want to join forces with other organizations, other people, and to improve it even further in the future. So I'm really happy from the contact and from getting to know so many of you. Muchas gracias. Buenas noches. Buenas noches. Hasta luego.